Hello, this is Matt Gaskill, Philosophy 160, presenting problem 2.1, problem 9.2.1. And in this problem, we're being asked by the tree method to show that identity is transitive according to the second order definition. And we're going to do that by showing that the following arguments are valid using the tree test. And so we've got from the book two premises. The premise one, which is universal P, PA only if PB. And the second premise, universal P, PB only if PC. And then the denied conclusion, universal P, PA only if PC. So that's the conclusion. We deny it. We put a negation in the front of that statement. And so lines 1, 2, and 3 are our basic setup for the tree, and essentially just copied from the problem in the book 9.2.1, with the exception of denying the conclusion. And so the first step is to swap the position of the negation. So instead of being in front of the quantifier, we're going to go ahead and swap it to the right of the quantifier. And when we do that, we have to exchange the universal quantifier for an existential. And so that's how we end up with line 4, is we simply just take line 3 and swap the denial from the left to the right, and then change the quantifier from universal to existential. And then the rest of the line is just copied down from line 3. And since we've got an existential statement, usually the next best step is to go ahead and instantiate that line and go ahead and consume it, get rid of that line so we don't have to worry about it anymore. And so what we have to do is with an existential quantifier for a predicate, we have to select a new predicate that does not already appear in the tree. And since we don't have any predicates that appear in the tree, they're all just these variables P, we can choose one. And so if we use the example that at the bottom of page, or near the bottom of page 126, they'll use the name K for the particular instantiation. So we'll do the same thing. We're just going to let P replace P with K. And so we'll drop the quantifier. We remember to bring down the negation, and then bring down the line and replace all instances of P with K. So we've got line 5, which is the instantiation of line 4, and we've got not K only if KC. And that one's a nice form, because we can use rules of inference without branching. And so in this case, we've got the form a negation of implication. And so we're going to go ahead and use that rule and take this line 5, and then we'll break it down into lines 6 and 7. And so our O in this case is KA, and our triangle is KC. And so the negation of implication rule shows us that we need to have a negated triangle. And so we've got lines 6 and 7, and those both come from line 5 using negation of implication. And then the next step we're going to take is we're going to instantiate line 1. And in this case, we're going to use the example at the top of page 127, where we denote the instance of the predicate variable P by the expression A equals. And so what we're saying here is we have this kind of generic predicate. So in the example here in line 1, PA, we're going to essentially say that P is, we're going to replace that with A equals. And so we're going to say that the P, if you want to say it in English, A is. And so that's what we're saying here. We're saying that P is just going to stand in for A is. So A is A, and then only if A is B. So we're just swapping out that P predicate portion for the A equals. And so here we're going to instantiate from line 1 this line 8, and we're going to swap out the P with A equals. So wherever we see P, we're just going to instantiate that with A equals. So A equals A, or A is A, only if A is B. So we've just brought this line 1 down, swapping out the P's with A equals. Now, this is an undenied material consequence. So we use the rule of implication, the rule of inference, implication, and that's going to go ahead and branch this line using the dominant operator only if. And so that's this rule here. And so the antecedent needs to be negated. And so A equals, the negated A equals is A doesn't equal. In this case, A doesn't equal A. And then our triangle is not denied. It just gets copied straight down without any change. So A equals B just becomes A equals B. Now, A doesn't equal itself is a contradiction. And so that automatically closes the line or the branch. And now we got this A equals B. And so the next thing that we want to do is instantiate line 2. And so we do the same thing that we did for line 1. We just swap out A equals for P. So wherever we see the P, we're going to say A is B, and we're going to say A is C. So that's what we've got here. Just wherever we've got the P, we've just swapped it out for an A equals. And again, it's the same form as on line 8. We have this undenied material consequence. So we repeat the rule of implication. We swap out or we deny the antecedent. And so instead of equals, we have not equals. So A does not equal B. And then the consequent, the triangle here, it just gets carried down without change. So A equals C. Now, in the case of line 11 here, we have A does not equal B. But if we follow up the branch, we get to line 9, which says that A does equal B. And so we've got a contradiction here. That contradiction then closes the branch. And now here on line 11, we are told that A is C. So they're identical. A equals C, C equals A. They're identical. And so what we do is we go up to line 7, where we have this denied KC. And since we know that A equals C, then we can copy that line 7 down to line 12 and just replace the instance of C with A. And now we end up with a line that says not KA. Well, we've got, if we follow up the tree, we've got line 6 here, which says indeed KA. So we've got KA and we've got not KA. Those contradict, and that allows us to close the branch, close the tree. And so that then shows a valid tree, which answers problem 9.2.1 to demonstrate that the argument is valid. So from line 1 to line 2, therefore, or so line 3, valid argument. All right, if you have any questions, hit me up on Pronto. All right, thank you.